Before we talk about improper integrals, I would like to review the fundamental theorem of calculus. In particular, I want to point out two important assumptions. So we start by assuming that f of x is continuous and that it's continuous on the closed interval from a to b. Then if capital F has derivative little f, we can find the definite integral of little f on the interval from a to b as capital F of b minus capital F of a. So what we want to consider in this next group of videos are situations where either one or both of these red underlined conditions don't hold, and this leads to what we call an improper integral. To start, in this video, I want to focus on the second underline there, and I want to look at improper integrals of the type that involve a limit of integration that is infinite. So this can come about in several different ways. In this video, I simply want to define how we would handle these, and in the next video, we'll go through some particular examples. So these are improper integrals involving infinite limits of integration. Okay, so first of all, this could come about in the way that we have a finite number in the lower bound and an infinite upper bound. So FTC did not address how we would integrate with this infinite upper limit of integration. So what we want to do here is treat this as a limit. So if I were able to integrate from that same value a to some value b, so b is like a placeholder here, then what we can do is apply FTC to that integral, which would give us an answer that's dependent on b, and then we'll take the limit as b goes to positive infinity. So once we've defined it this way, we can now discuss the notion of an integral converging or diverging. So we're going to say that the integral converges if the limit described above exists and is finite. Otherwise, we say that it diverges. So we can get that an integral here diverges because perhaps this limit doesn't exist, or even when it does, if it's infinite. So a similar type of integral is if we were instead to integrate from minus infinity to some fixed constant b. And the same kind of approach, we would integrate from a to b, where a now is some placeholder. Our answer would depend on a, and we could send that a value to minus infinity. And we have the same terminology. This integral, we would say, converges if the limit exists and is finite. And then otherwise, we're going to say that it diverges. And then the last thing to consider with regards to infinite limits of integration is that we could encounter a situation where we integrate from minus infinity to positive infinity. What we'd like to take advantage of is the fact that we, at this point, would know how to deal with a single infinite limit of integration. So what we could do is break this up as the integral from minus infinity to some value c really could be anything, plus the integral from that same value c to positive infinity. So that we could start by that. And then now I could use numbers 1 and 2 to evaluate these individual integrals. So this first one we would express as the limit as a approaches minus infinity of the integral from a to c. And then we could tack onto that the limit as b approaches positive infinity of the integral from c to b. Now here, we have to be a little bit careful. We have these two different improper integrals involved. So when we're talking about the original integral. So just to be clear, when I say the integral here, I mean this one. The integral converges only if both integrals on the right converge. So we've introduced the two new integrals on the right, and importantly, we need both of those to converge. So here we'll say, again, otherwise it being the original integral, diverges, but importantly, that means that as soon as you find that either one of these on the right diverges, you can stop and say that the original integral diverges.